This is an important learning objective because you're going to see this again in portfolio management, and you see a lot of this at level 3, or we work a lot with expected value and expected or the level of risk or expected standard deviation of the portfolio at level 3. We don't calculate, we're just given these, so we really need to know how these things came about. Calculate and interpret the expected value, variance, standard deviation, covariance, and correlations of portfolio returns. So we're going to calculate the expected value of the returns for portfolio returns, expected value, the standard deviation of those returns, the covariance among the assets in the portfolio, and the correlations among the assets in the portfolio. The expected return on the portfolio is just a weighting. Each asset has a weighting in our portfolio multiplied by the expected return on that asset. It's just a weighted average. We've seen that before. What's different here is this return is an expected value in itself. So it's the weight that we have on this expected value, and this expected value is also a random variable, which is the probability of a return given a particular scenario times the return in that scenario, times the probability of the return on, and I just have asset 1, R1, because this is R1, under scenario 2, times the return we expect under scenario 2, on and on, all the way through n scenarios. So we may take a security and say, well, here's different values, different returns you could have with the different probabilities, and that will be the expected return on security 1, which goes into our portfolio, expected return on security 2, or asset class 2, which goes into our portfolio. And then, of course, all of those returns will have different weights in our portfolio, and we'll multiply those weights to get the expected portfolio return. So let's calculate expected return on a portfolio. Let's assume that we are going to allocate our money as follows into 3 ETFs. One ETF is going to track the S&P 500, one ETF will track corporate bonds, and one ETF will track an index for Europe, Asia, and the Far East. 50% of our funds will go in the ETF for the S&P 500, 25% of our funds into corporate bonds, and 25% into the other index. We expect these returns from these particular markets. The S&P 500 we expect will return 13%, 50% of our money will be in there, etc. What's the expected return on the portfolio? It'll be the weighting, which is basically the probability multiplied by the expected return for each asset class, and we'll call these different asset classes. We expect that that portfolio with these weightings will return 11.75%. Nice and easy. This is a measure, the expected return on the portfolio, is a measure of our expected reward. If we have reward, we must have risk. They go hand in hand. No risk, no reward. Well, how do we measure risk? That is the variance, the expected variance of the portfolio, and to calculate that, we're going to need all the expected returns and all of the covariances. When we calculate covariance, we need expected return because the covariance is the cross product of the deviations from the expected value. So let's not worry about this whole formula first. It is going to require covariance. You'll recall covariance is just the deviation. Let's say we have 3 asset classes. This is asset class 1, this is asset class 2. It's the deviations on one asset class from its expected value multiplied by the deviations on the second asset class from its expected value, and that's all n over 1. If they are the same asset class, if this is asset class 1 and this is asset class 1, what do we have? We have the deviations on asset class 1 squared over n minus 1. That's a variance. So the covariance of an asset with itself is its own variance. So here we are. We have 2 summation signs, I equals 1 to n, j equals 1 to n, weighting on the first asset class, weighting on the second, or whichever asset class it happens to be, times that covariance. Down here, I'm going to say, let's assume we have 3 assets, R1, R2, R3. So let's do that. R1, R2, R3, and we'll draw R1, R2, and R3 across the top. So we're going to fill out what's called a variance-covariance matrix. So if these 2 summation signs, when we first start, this will be I equals 1, j equals 1. So this will be the weighting 1 times the weighting 1, which will give us the weighting 1 squared. It'll be the covariance of asset 1 with the covariance of asset 1. Well, that's a variance. So this will be a variance. And there it is right there. There's the variance of asset 1. The second j, the second term here, j will go to 2. So it'll be 1 and 2. R1, R2, it'll be this amount in here. It'll be the covariance between this. And then J will go to 3. It'll be R1, R3, and that'll be a covariance. Then I goes to 2, J goes back to 1. We have 2 and 1, R2, R1. That'll be a covariance. However, the covariance of R1 with R2 is the same as the covariance of R2 with R1. So we have 2 covariances. 2 covariances. And that's why all these covariances are 2. In a variance-covariance matrix, all the entries on the diagonal will be variances. The amounts above the diagonal will all be covariances. Same with the amounts below the diagonal, they'll all be covariances, but these and these will be the same. So you'll have an equal number of covariances, but unique covariances, we only need one side of the diagonal, which is why we multiply each of the covariances by 2. Here's a covariance between R1 and R2, R1 and R3, R2 and R3, but they'll happen twice, so we multiply by 2. W1, W3, there it is right there. W1, W3 times the covariance. W1, W2 times covariance of R1, R2. That's just this whole term. I just want you to see how that all comes together so that when we look at the 2, say, why are we multiplying by 2? Is because there'll be 2 covariances. This covariance, R1, R2, is the same as R2, R1. So rather than write out 6 terms, we'll just say 2 times this term. Exactly. So this is for 3 assets. Notice that when we're calculating portfolio variance, what are we doing? We have the sum, the weighted sum of 3 variances and 6 covariances, or 3 unique covariances twice. Let's have a look at Exhibit 11. So this is important. It'll help you when you get to portfolio management, and especially at level 3. It's heavy on portfolio management. The inputs to portfolio expected return and variance. You need expected returns on each asset class or each security. Let's say you're building a portfolio of 6 stocks. You're going to need expected returns on those 6 stocks, and you're going to need the covariance and variance between all of them. So you'll need a variance for each of the 6, and you'll need all of the covariances, because how they move together determines your risk. This goes back to positive or negative correlation between assets. If we have assets with 0 correlation, it means they're going to be unrelated to each other. The risk of the portfolio breaks down to just the weighted variances on that one. We'll see a little bit more of that later. But here's 3 asset classes. We're going to need a covariance matrix. And the way we read the covariance matrix, notice the bold entries. These are all variances. A covariance of asset A with asset A is a variance. So when we see RA, RA, even though it says covariance, that's a variance. A variance is a covariance of an asset with itself. There it is, RB, RB, RC, RC. This is the covariance of RA, RB. This is the covariance of RB, RA. These are the same numbers. So in this matrix, this 3 by 3 matrix, there are 9 entries. 3 are variances, 6 are covariances, but there are only 3 unique covariances. Okay, so let's look at some properties here of portfolio risk or portfolio variance. So that we are prepared when we see this in portfolio theory. And this we draw a lot upon this at level 3, so it's good to get a good handle on it now. The variance of the portfolio is going to be a function of all of the variances and covariances of the individual asset classes or securities within the portfolio. Variances are always greater than 0. So whenever we add an asset class to a portfolio, its variance will add to portfolio risk. However, it may have covariances with other asset classes that actually reduce risk, because covariances can be less than 0 or greater than 0. I'm going to put an equal sign in there so we can say less than or equal to 0 or greater than 0. And remember, the covariance, the sign of the covariance determines the sign of the correlation. If the covariance is 0, it adds no further risk to the portfolio. If the covariance is negative, it actually reduces the risk of the portfolio. So we're going to make a major point here, but then I'm going to qualify it. We're going to read a paragraph from the reading, and I want to make sure that you understand this point very clearly. Here's a major point. By selecting assets with 0 or negative covariance, portfolio risk is lowered. So let's look at the at that paragraph, and I just want to make a point very clear here. Right, so in the reading, when you get to equation 18, It is the long paragraph just after that, and we'll start right here. If the covariance terms were negative, then a negative number would be added to 132,625. This 132,625 being the sum of just the variances in the example that's given. So portfolio variance and risk would be even smaller while expected return would not change. While expected return would not change. Okay, I'm going to revisit that in a second. For the same expected portfolio return, the portfolio has less risk. This risk reduction is a diversification benefit, meaning a risk reduction benefit from holding a portfolio of assets. The diversification benefit increases with decreasing covariance. Not true. That's not entirely true. Let me explain why. If that were true, then it would be my job to find assets with the greatest negative covariance. And remember now, the sign of the covariance determines the sign of the correlation. So the greatest covariance, negative covariance I can get is one that creates the lowest negative correlation, -1. Well, to get a correlation of -1, I would remove all risk from the portfolio. If I remove all risk, I cannot make the same return. No risk, no reward. A portfolio in which all risk is removed would earn the risk-free rate. It would not earn the same rate of return. So we got to be careful with what they're saying here. Portfolio variance and risk would be even smaller while expected return would not change. That is not entirely true. If you found asset classes that had negative covariance, they would not have the same expected return as other asset classes with positive covariance. So no, you would not get the same expected return. You would get a lower return simply because if an asset has negative covariance, it means that when one asset's return is above its mean, the other asset's return is below its mean. The more negative it is, the more wider that spread happens to be. So you may end up with assets that have great returns and add an asset with a negative covariance that actually may have a 0 or a negative return, thereby reducing the very return that you had taken risk to get. So we got to be careful about that statement. In and around 0 on the correlation is maximum diversification. As we get more and more negative on the correlation, we start to actually change the portfolio return because it's going to be difficult to find asset classes that have those correlations without affecting the entire portfolio return. Just so that when you get to portfolio management, and especially at level 3, you don't start getting confused by that statement saying, I thought that we could get the same return if we just lower our, and we can continue to lower our risk if we find assets with negative correlation. You can do that. You can use options and forwards to completely remove the risk of an asset class. You'll get 0 return. When you get to derivatives, you'll see how that's done, where you can actually remove an asset class from the portfolio without actually selling it by using derivatives, but you give up all the return. I want to be clear on that. Let's continue. All right, so I've shown you the variance covariance matrix. We've drawn one out on the previous screen. Let's talk about the relationship between n and the number of variances, covariances, and distinct covariances that we would get. For n securities or n asset classes, typically we construct portfolios out of asset classes. Because we have to calculate covariances for every cross asset, when you get to the security level, if you got 30 or 40 securities, that is a lot of estimates that you're going to have. So typically we do it at the asset class level. So you have n securities or n asset classes. We'll let n equals 5 in our example here. You will get n variances. That makes sense, right? You'll have 5 variances. You will get n squared minus n covariances. Remember, if you have 5, that means you're going to have a 5 by 5 matrix. So a 5 by 5 matrix, that's n squared, will have 25 entries, but if 5 of those are variances, you'll only have 20 covariances. Well, that's 25 minus 5, n squared minus n. You got 20 covariances, but if you divide that by 2, you get 10 distinct covariances because each covariance is copied somewhere else. So if you have the covariance between asset 1 and asset 4, it's the same as the covariance between asset 4 and asset 1. That's 2 covariances, but it's 1 distinct covariance. Now that we have covariance, we can move to correlation. Correlation is the covariance of an asset divided by the 2 standard deviations. Now, I want to show you something here which backs up the point I said a little earlier that if we do find an asset with a correlation of -1, we will eliminate all return and all risk. Let's assume this covariance is between asset 1 and asset 1. Well, what would that be? That would be a variance, right? So we have a variance in our numerator. Well, this would be the standard deviation of asset 1 multiplied by the standard deviation of asset 1. What do we have in our denominator? We have a variance. They cancel out. We get a correlation of 1. So if we take an asset and we sell a forward contract on that asset, we create an identical negative asset. There's a correlation of -1. That reading, that paragraph would tell us that that would be ideal, but every return we would make on the asset, we would exactly lose on the forward contract, thereby creating zero gain. And when you get to derivatives, you'll see that the forward contract is priced using the risk-free rate, and that's all we would make. So that statement in that paragraph is misleading. I need to stress that. I don't want you to think that, hey, all we got to do is keep getting closer and closer and closer to -1 for maximum diversification. No, you end up with perfect hedges. 0 is what you're aiming for, in and around 0. All right, let's get back to this. Let me back out some of this writing that I did here so that I can use it to draw some other things if I need to. All right, so there's our correlation. It is the covariance divided by the two standard deviations. Well, if we multiply by the denominator, we can isolate the covariance to one side is equal to the correlation multiplied by the two standard deviations. So I've reproduced here for you Exhibit 12 from the reading and Exhibit 13 from the reading. Exhibit 12 is a covariance matrix. Exhibit 13 is a correlation matrix. I'm going to show you how you get these numbers from these numbers, and we'll just take 189. So this is let me get a better color here. That's a variance, that's a variance, that's a variance. If we're calculating the correlation of an asset with itself, we should get correlations of 1, right? I've already shown you that. Let's get this correlation of 0.45 from this covariance. Well, if we're calculating correlation, which is over here, what is it? Covariance is in the numerator, so let's put 189 in the numerator. What's in the denominator? The standard deviation of the two assets of which this is a covariance. Well, this is S&P 500 crossed with the MSCI index. So the S&P 500 has a variance of 400. We don't want variance, we want standard deviation, so it's 400. We take the square root, or the power of 1/2. And the MSCI index has a variance of 441, so we take the square root of that. That'll be the standard deviation of that asset class. That's 189 divided by 20 times 21, or 0.45. There you go right there. I will let you recover all of the other numbers. We know how to get this diagonal. We know how to get the 0.45. There's only 0.25 and 0.2 to go because the ones below the diagonal are exactly the same as the ones above the diagonal. Calculate and interpret the covariances of portfolio returns using the joint probability function. We've already calculated the covariance of assets within a portfolio based on their expected return. So we have, let's say, 3 asset classes, 1, 2, 3, and we have expected returns for each specific asset class, R2, and expected return R3, and then we can calculate covariances based on these expected returns. What this LOS is saying is, well, hang on a second now. What if instead of an expected return, you had a situation where you had scenarios first, and depending on the scenario, you had an expected return on 1, 2, 3. Depending on another scenario, you had a different expected return on 1, 2, 3, and of course down here as well, R1, 2, 3. How would you calculate a covariance based on that? Again, previously we already calculated the covariance, but we had one expected return. This is saying for the joint probability LOS that we're on now, the covariance given a joint probability function, how would you calculate the covariance given this? So let's just lead in to what we're given a formula in this particular section, but let's see if we get there on our own. This was the formula for covariance that we're aware of. It's the sum of the cross products, and R is return. There's asset A and asset B. The cross products of the return divided by n minus 1. If we expand it out, we multiply each cross product term by 1 over n minus 1. Well, these are the weights, all equally weighted. Well, we can turn these weights into probabilities, and when we turn in the probabilities, we have the concept of a joint probability, and there's the joint probability. The probability of the return on A and the return on B happening together. So it's the joint probability of those based on the different scenarios that we may have. And of course multiplied by the cross product. So again, this is nothing more than probability multiplied by the value of the cross product, or the value of whatever we're multiplying it by. So it's still probability weighted, except now it's joint probability weighted. If the returns are independent, we know from the multiplication rule that the joint probability is nothing more than the multiplication of the two probabilities. Now, this is an important point. Independence is a stronger property than uncorrelatedness. So if we have uncorrelated variables, this formulation holds. Because if it holds for independence, and independence is a stronger property than uncorrelatedness, then it holds for uncorrelated variables. Things look better when we look at particular things. The important thing here, I and j, where we see the summations from I to j, these are now scenarios. As I just said up here, they're different scenarios. Let's look at Exhibit 15, Exhibit 16. We're given a very simple joint probability function. All right, so here we are. It's a really simple joint probability function. You see a bunch of zeros in here. They don't have to be zeros. The important thing is all the probabilities in all the cells must add up to 1. So this is 20, 50, and 30. That adds up to 100%. If this wasn't 20, if this was 10, then we'd have to find 10 in one of the other zeros. Anyways, what this is saying is we have three scenarios: good, average, and poor. If we were in a good scenario, the return on A would be 25%, the return on B would be 20%, with 20% probability of having a good scenario. If we have an average scenario, we have a 50% probability of having an average scenario. Return on A would be 12, return on B would be 16. You see, this is moving away from the idea of having an expected return for an asset class to having expected returns based on possible scenarios across asset classes, which means you would need these joint probabilities. So we have to calculate a covariance based on this. And what do we need for covariance? We need expected values. So the first step would be, what's the expected value for the return on A and the expected value for the return on B? Here are returns, here's the probabilities. So we just multiply the probability by the return. So for A, it would be 0.2 times 25% plus 0.5 times 12% plus 0.3 times 10%, which we see is done down here. We get 14%. For B, it would be the same thing. 20% times 0.2, 16% times 0.5, and 10% times 0.3. And we see that that is done across here. We get 15%. So now we calculate the deviations, and that is done in 16. So deviations for Bancor and New Bank. So Bancor is down here, is RA. New Core is RB. We knew the expected value for Bancor was 14. So the three scenarios we had, let's go back up. You can see it's 25%, 12%, and 10%. So let's do that. 25 minus 14, 12 minus 14, 10 minus 14. We do the same thing for the deviations on New Bank. These are the two deviations. This is the product of the deviations. 25 minus 14 is 11. 20 minus 15 is 5. 11 times 5 is 55. That's the deviations. Here's the probabilities, 20, 50, 30. Where do we get those? 20, 50, 30. It's a really simple example because they're just showing you how something like this could be done just to demonstrate the application of it. But, you know, they're not going to give you a really complex example. That's not the point. So there's the probability. So you just multiply them. 0.2 times the cross products is 11. 0.5 times the cross products is negative 1. 0.3 times the cross products is negative 6. Add them up. What do you get? We get 16. That's it. We're going to look at some applications now that the normal distribution is sort of underpinning. Define shortfall risk. Calculate the safety first ratio and identify an optimal portfolio using Roy's safety first criterion. So safety first rules focus on shortfall risk. And shortfall risk is the risk a portfolio value or return will fall below some minimum acceptable level over some time horizon. So let's look at the formulation for this. Let R sub L equal the minimum acceptable level of return that we would want. The SF, safety first ratio, which will be a z-value, by the way. This formulation here returns a z-value. Look at what we have in the numerator. We have the expected return on the portfolio minus the minimum level that we want. That is the distance between the two, divided by the standard deviation. That will give us a z-value. The objective here is to maximize this ratio. And the optimal portfolio will minimize the probability. Notice that whatever z-value we get here, it enters here as a negative value because the return on the portfolio should be higher than the minimum level. This will be a positive number, but we want, just to draw it out, it'll be a positive number, but we're looking for this. This will be RL, and this is the return on the portfolio, the expected return on the portfolio. So this should be a negative z-value. However, because our goal is to maximize this ratio, rather than the numerator being RL minus ERP, which would give us the negative z-value, we flip it around and say, let's maximize the safety first ratio. If it were the other way around, we would then be minimizing both. It would seem to make more sense to me, but there it is. All right, let's put it in practice. Let's say our minimum acceptable level of return is 2%. We have portfolio 1 and 2. Portfolio 1 has an expected return of 12%, standard deviation of 15. 2 is 14 and 16. Let's calculate the safety first ratio for portfolio 1. It is 12 minus 2 divided by 15, or 0.666 repeated. That enters in as a negative z-value. 25.25% probability that the portfolio will earn less than 2%. For the second one, 14 minus 2 over 16 is 0.75. Since the goal is to maximize that ratio right away, we know we're okay. But let's just see if it does minimize the probability. That enters as a negative z-value because, of course, it is below the mean, right? 227, or 22.7% probability of falling below 2%. So if our definition of risk was shortfall risk, we would be taking portfolio 2. If our definition of risk was volatility, notice that portfolio 2 is more volatile than portfolio 1. So if we were defining risk in terms of volatility, we'd be taking portfolio 1. But if I said, look, there's a certain return I have to get, and I'm concerned about left tail risk, about shortfall risk, I want to minimize that, we would now be taking portfolio 2. When you get to level 3, you have to be able to look at portfolios and say, first of all, what is my definition of risk? And given my definition of risk, which portfolio satisfies it? So it's a two-step process. You have to first figure out, am I concerned about shortfall risk, or am I concerned about volatility of the portfolio? And then from there, you would determine what portfolio you want. So you're going to see this again. A note to make, you're going to see this in this level as well. If RL is the risk-free rate, if our lowest expected or lowest acceptable level of return is the risk-free rate, the safety first ratio is identical to the Sharpe ratio. Let's look at example 7. All right, the safety first optimal portfolio for a client. You're researching asset allocations for a client in Canada with $800,000 portfolio. Although her investment objective is long-term growth, at the end of a year, she may want to liquidate $30,000 of the portfolio to fund educational expenses. If that need arises, she would like to be able to take out the $30,000 without invading the initial capital of $800,000. The table below shows 3 alternative allocations. So she wants to take out $30,000 in 1 year without touching the $800,000. So in 1 year, we have to return at least $30,000 off the $800,000. We have 3 portfolios, A, B, C, with standard deviation of return. 27, 8, and 20. Address these questions. Assume normality for questions 2 and 3. Given the client's desire not to invade the $800,000 principal, what is the shortfall level? Use this shortfall level to answer question 2. It should just be 30,000 over 800,000, right? 30,000 over 800,000 is 3.75. If you return 3.75, at the end of the year, you'll have 830. You take out the 30, you haven't invaded the capital. So that is our that'll be our safety first criterion is 3.75, and according to the safety first criterion, which of the 3 allocations is best. So we just have to calculate the ratio. the safety first ratio, 25% minus 3.75 divided by 27, 11 minus 3.75 divided by 8. You get what's going on here, right? So let's see what we have. So here it is here. Here is the deviation from the expected portfolio to the lower bound divided by all the standard deviations. We get 0.78, 0.90, and 0.51. Our goal is to take the highest one. We're maximizing this ratio, 0.906. So we're going to take allocation B. And for number 3, what is the probability that the return on the safety first optimal portfolio will be less than the shortfall level? And we know that we enter in this z value as a negative value in the norm.s.dist function call for Excel. Our z value will be negative 90625, which, it's really wordy down here in saying that that's what we do. You can see it right here. And it will return 0.1814 or 18.14%. That's it.